All right, welcome ladies and gentlemen. This is video number 1 in our matter unit. So you're going to need your note packet open to where it says video number 1. And in this video, I'm going to be talking about substances, specifically elements versus compounds. So what is a substance? A substance by definition is matter, so something that has mass and occupies space, that has unique properties in composition, i.e. a substance is something with a fixed chemical formula, meaning it is always the same. For example, water. That is a fixed chemical formula. It is always the same. It's always 2 H's and 1 O. That's what that formula means. Water is a substance. It's always the same. It's a fixed formula. Substances, by definition, because they have this fixed formula, because they are always the same, they are pure, meaning it's 100% of the same thing. Sand would not be a substance because sand is not pure. There's lots of different components of sand, and they can vary from beach to beach. So sand is not a substance, but water is, because it's always the same. The 2 types of substances are elements and compounds. So substances can be divided into these 2 categories, elements and compounds, and they're both considered substances because they both have this fixed formula. This fixed formula is very important to the definition of a substance. So first up is an element. An element is a pure substance, so pure, again, it's constantly the same thing, but it's only made up of one kind of atom, just one type of atom. So just to be very, very clear here, elements have a fixed formula, not an unfixed, meaning like potassium, that's an atom, so it's always K. It's always the same formula. Elements cannot be broken down by physical changes, meaning that if you were to do a physical change on an element, you wouldn't change it in any way, shape, or form. The element itself would stay the same. Other properties, if it was a mixture, that might change, but the element itself would stay unchanged. Also, elements cannot be broken down by chemical changes. What that means is if you were to do something like a chemical reaction, that's my abbreviation for reaction, RXN, the element itself would be unchanged. Maybe other things would change, but if you were to do a reaction involving hydrogen, the hydrogen itself would not be changed at all by the chemical reaction. And this is a big, big point about elements. Notice that there's no physical change or chemical change that we can do to an element that would actually alter it. The element would stay unchanged by physical and chemical changes. So just as an example of this, if you were to start with a reaction with aluminum, this is saying that, well, if you can't change it by a chemical reaction, that means that you have to end with aluminum, that the aluminum wouldn't get changed into, let's say, oxygen. Right? It has to stay as aluminum. It's not altered. Chemicals are always represented by 1 or 2 letter symbols in the periodic table. The first letter is always capitalized. The second letter is always lowercase. So this is a way of determining how many elements you actually have, how many capital letters are in your compound or your formula, and that's how many different elements you have. So first letter is always capitalized, and if there's a second letter, it's going to be lowercase. So for example, if we have AL, notice that it's a capital A and then a lowercase l, and then if we were to do a reaction where we combine it with oxygen, right, that's O2, so that's just one symbol, so it's just uppercase, and the compound that we get from this is actually called aluminum oxide, but again, it's a combination. Notice that the elements themselves are staying unchanged here. They're not altered. It's still aluminum and still oxygen. Monatomic versus diatomic. There are 2 types of elements on the periodic table, monatomic and diatomic. Mono means 1, di means 2. So the word diatomic quite literally means 2, that's the di. And then atoms, atomic. What are diatomics? Well, basically there are certain elements on the periodic table that are super unstable on their own, and they always need a buddy. They can never be found as a single atom. They have to be paired up constantly. Now, whether that means they're paired up with another element or if they're paired up with themselves, but they have to be paired up. They have to be combined. They're never going to be on their own. And there are 7 of these elements that are on the periodic table, and These 7 diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, and bromine. And there's a little mnemonic for remembering this, that these 7 elements are diatomic, which, by the way, means that you would find it not as H, but as H2, not as N, but as N2. That's the di bit. That's where we're actually getting 2 H's, 2 N's, 2 O's, 2 F's, 2 chlorines, 2 bromines, 2 iodines. That's what the diatomic means. They always have to pair up, whether they can pair up with something else or pair up with themselves. They always have to pair up because it makes them more energetically stable. It gives them a lower energy. The mnemonic is H-NOF down. So that's the mnemonic device, H-NOF down. And if you have a look at your periodic table, you'll notice that the N, O, and F, which are over on the right and at the top, and like hydrogen's on the left, but if you pair it with that, the H-NOF, the N, O, and F are in a row, so that's our NOF. And then down, if you look directly below the fluorine, the first 3 elements underneath that are chlorine, bromine, and iodine. So it's like that little corner of the periodic table, so the NOF and down, plus hydrogen, these are your 7 diatomic elements. So again, that means that these elements, they're never found, it's not H, it's H2. It's not O, it's O2. It's not Cl, it's Cl2. Now these elements can be singular as long as they're paired up with something else. So for example, NaCl, right? The chlorine is not Cl2 in NaCl. We know the sodium chloride, right? This is table salt. But the chlorine is paired with something. So the chlorine always has to bond to something. And if it's not bonding to another element, then it's bonding to itself. That's what these diatomic elements are. Now, particle diagrams. Particle diagrams are a big part of chemistry, sort of trying to draw on an abstract scale, what do these atoms look like? A monatomic element, so it's one type of atom, right? One type of atom, but it's monatomic, which means that it's not paired up. A drawing for a monatomic element would probably look like this. Notice that they're all the same. That goes to the fact that for an element definition, you have one type of atom, but the monatomic means mono, so just one, meaning it's not paired together. So notice that they're completely separate, right? This one is totally separate from this one, which is totally separate from that one. A diatomic element, on the other hand, would look like this. So again, this is an element because one type of atom. Notice this still applies here. There's only the orange ones, one type of atom. However, the diatomic bit, notice that they're paired up. Right, paired together. They have to. So this would be our H-NOF and down. This could be a hydrogen, but it's still an element, and that's the really, really big important bit. This is absolutely still an element. It's because there's only one type of atom. A compound, on the other hand, is also a pure substance, but now it's made of more than one type of atom. So a compound is going to have more than one atom in it, and these 2 or more elements, they are combined by a chemical change, so they are chemically bonded to each other. And a compound will always, always, always have a fixed chemical formula. So for example, water is an example of a compound because there are 2 types of elements, 2 types of atoms, there's H and O, but it's a fixed formula because we have 2 hydrogens for every 1 oxygen. It's always the same ratio, it's always the same formula, it's always the same combination. Compounds cannot be broken down by physical changes, but they can be broken down by chemical changes. So you can do a chemical reaction. For example, you could take water and you could break it down into the hydrogen and the oxygen. This is a chemical change. You are altering the components of the system, but you can break down a compound through a chemical change, but you cannot break it down through a physical change. A physical change would be, for example, water, liquid, becoming solid water or ice, but it's still water. That's a physical change. So it's unchanged by physical change, but it is altered by a chemical change. And the key thing about compounds is that the properties of a compound are actually going to be totally different than the properties of the individual elements. For example, NaCl. I love to talk about this one. Sodium explodes when you put it in water. Lights on fire in water. Ridiculously dangerous. That is a nasty metal right there. Chlorine gas is poisonous. It's toxic. It was used in chemical warfare. You might put chlorine in your pool to kill things. Like, chlorine is a poison. But when you combine them into a formula, into NaCl, you get something that is so safe, so not toxic at all, that you put it on your food and you ingest it all the time. And it's just sitting out on your table at home. So the properties of a compound are totally different from the properties of the elements that go into it. If we're drawing a particle diagram of a compound, first of all, you have to have two types of atoms to draw a compound, but you have to have a fixed ratio or pattern, meaning all of your compounds have to look exactly the same. So for example, these would be two examples of compounds. So this right here is a compound, and notice that, again, the two types of atoms, but each of these has the same ratio. It's always 2 blue, 1 green, 2 blue, 1 green. Likewise, this would also be a compound because notice two different types of atoms, but each one of these, when we compare it to the other, they're all the same ratio. That's the fixed formula. So we will practice with this in class.